accepted.
Hello everyone, and welcome to my talk about empowering your development with functional programming, understanding, and practice. First, a little bit about myself. Try to keep it brief because we have a lot to talk about today. So my name is Cies van Ven. As you may be able to tell by my accent, I'm from the Netherlands. In my career, I did a lot of Java, then kind of switched to Kotlin, even dipped into a bit of Scala, and now doing Java again. And I try to be a bit of a functional programming advocate. Because I noticed there are basically two camps of people. People who really love functional programming, and people who really hate functional programming. And I try to convince the latter to give functional programming a chance. And hopefully after the end of the talk, you may think that you're more of a functional programmer than you might actually think you are. So what will we talk about today? Currently we're doing the introduction. We're going to talk a bit about what functional programming brings to us. And the main four topics are composition, state management, error management, and side effect management. Out of these four topics, I would say the only real functional programming thing is composition. The other three are mostly talked about when talking about functional composition, but I find this a bit weird, since no matter the language, no matter the paradigm, you kind of have to deal with these three topics. So why are they usually mentioned when talking about functional programming, but not really when talking about object-oriented programming? Well, this is my current theory for that. In mathematics, we have some ground rules. We call those the axioms of mathematics. And the job of mathematicians is, given those rules, they kind of have to figure out what's possible within the universe. The exact opposite of that are physicists. They look at our current universe and they're slowly trying to figure out what the underlying rules are. And this also kind of applies a bit to software engineering, where on the bottom we have the academics, like more theoretically minded people. They basically, at their education, learn the ground rules of software engineering. And on the top, we basically have most of us, including me, who basically just learned how to be productive given the base of programming, and slowly trying to figure out what the underlying rules are. So I think it's more talked about in a functional programming way, because yeah, the academics get these things taught at school, and we kind of have to figure those things out. But they apply to all paradigms and all languages. So what does functional programming bring us? Well, one thing, it really focuses on reusability. Object-oriented programming often gets talked about how reusable it is. Well, functional programming even goes a step up above that. And we're going to dip a bit into that when we're talking about composition. Another famous thing about functional programming is its terminology. We have all these nice fancy words like monads, monoids, functors, and such. And you don't have to worry about that. I'm not going to mention any of those words in this entire talk. But I do want to give you a bit of a tip, because actually learning this terminology made me a better programmer. Because your brain works in a weird way. If you don't have a name for a concept, it's quite hard for your brain to reason about it. But once your brain has a name for a certain thing, it becomes very easy to reason about it. So once you learn the names for certain concepts, it actually reduces a lot of cognitive load that your brain has to do. And also, it's very good for communication. And where functional programming shines is complexity management. So it tries to manage complexity. The problem with this, however, it doesn't always succeed in this, in a way that we have the scale of complexity, where on the one hand, we have extremely simple, almost trivial programs, like I just want to read the contents of a file and just print it to console. Well, on the other hand, we have these real big monolithic applications with huge domain models. And with very trivial programs, you can get away with a lot of things, and it doesn't really matter. But if your application is on that end of the scale, you kind of need those things. So the irony is that if you try to apply most of the things we're going to talk about today on those extremely simple programs, you're going to make them more complex. So these things shine there and shouldn't be used all the way on that side. And your software is probably somewhere in the middle. This is also the irony when you try to teach people about functional programming, that you want to use simple examples. You want to use examples on that side, but it's only effective on that side. So it's quite difficult to get good examples because simple programs get more complex if you try to use complex reducing things to it. So let's start with our first main subject, composition. So in composition, function signatures are key. So a function signature is composed of the input and output of a function. So here we have a getName function, which takes a person and turns it into a string. So the function signature is person to string. If you then have a length function that takes a string and reduces an int, we can now combine those two functions and create a whole new function that goes straight from person to int. So we're basically creating building blocks here, very small functions that do one thing. And basically, just like dominoes, we can chain them together. Because dominoes are just like functions. They have a number as input and a number as output. And alone, they don't do a lot. But we can chain them together to create very complex programs. And we can use this way of thinking to help us with problem solving. If I present with you the following problem, how would you solve this? Given a list of persons, sum the total age of everyone with a name starting with A. A second to think about it while I drink some water. Well, a lot of you may come up with something like this, where we have a variable total length, we loop over a list of persons, we basically do with an if statement check to select the people who start with an A, and then basically sum up the ages in our variable. But composition thinking actually allows us to solve this problem in a different way. Because if you actually look at this problem, it consists of 3 sub-problems. First, we want to select all the people that with the name starting with A. Then we want to get all the ages of the people. And then we want to sum all those ages. So we broke down our big problem into several smaller problems. And this is where I love the streaming API in Java. And this is where it shines, because it fully reflects this way of thinking. Because now we can solve it. We stream over a list of people. We select only the people who start with an A. We turn it into a list of ages, and then we sum it. Exactly like the 3 sub-problems we just identified. So the streaming API is a very powerful way to show this concept, and this is why I love the streaming API. If you're not fully convinced yet about compositional thinking, you may have used bash before. And one of my favorite features of bash is that pipeline symbol you see in the middle. This is basic function composition, because every program in bash has a byte stream as output and a byte stream as input, which means the inputs and outputs of every program match, and therefore we can compose them. So the pipeline symbol is actually just a composition symbol. So we can use small programs to do one thing to create really powerful programs indeed. And this is the power of function composition. We can also use this as a trick to help us be a better problem solver. Because programming is actually, most of the time, it's just problem solving. And once we solve the problem, we basically just need to implement it. And the trick here is that complex problems can be divided into sub-problems. To give a bit of an example of that, if you look at basically any use case out there, it's basically get some JSON, we put it in a program, and it will output some JSON back. So this is a very abstract way to think about software engineering. And we can use composition to break this down into sub-problems. If you write it down like this, we can then basically split our program up into two separate subproblems. So first, we probably need to parse the JSON and create some parsed input, then put it into logic that will then return JSON. And we can keep on doing this. We can split up our logic again to first, for example, enrich our input with some database stuff, turn it to enrich input, put into the logic, which returns JSON. And you can just keep on splitting the program until you solved basically, until you figured out all the subproblems of it. And now the only thing you have to do is basically chain those subproblems, and you finish the whole problem. And this is a very powerful way to think. Because the nice thing about this is, I didn't even mention any programming language. I didn't even mention any frameworks. I didn't even mention how many web services this problem has. All I'm busy with is breaking down the problem and solving the problem. And then I can choose the best way to actually implement this. So the key takeaways of composition is that most problems are actually compositions of smaller problems. And we can use that to actually increase our problem-solving skills. And the streaming API is a great way to reflect this, but also to practice this way of thinking. So that's why it's really important to use the streaming API. It makes you a better problem solver. So let's talk about state management, the big one. So what is state? State is basically all the values within your application. And state is very complex. To give a bit of an example, what if I would have a red car, and I don't like the color red anymore, I want to turn it into a blue car? Well, in real life, I would probably just paint the car blue. And object-oriented programming likes to emulate real life, so it will probably create some class like this with a getter and setter for the color. So the object-oriented programmer would just call the set the color and make it the car blue. A functional programmer would do it slightly differently. A functional programmer would take a very good look at the red car, create a completely identical copy right next to it, except for the color, then paints it blue, and then he destroys the red car. And now the functional programmer has a blue car. In real life, I wouldn't really use this strategy. But in programming, there's actually a benefit to this. Because if I ask my object-oriented car, what color are you? What will I get back? The thing is, it depends. Do I ask it early in the program, or do I ask it late in the program? Because the value changes over time. If I ask my function programming cars, either one of them, which color are you? I always get back the same value. And this is why mutable state is inherently more complex than immutable state, because it adds the complexity of time to it. And this is a very important thing. So that complexity of time causes a lot of very difficult problems, like race conditions and concurrency issues. But I don't really want to talk about those things today, because not a lot of people actually do concurrency or applications with a lot of concurrency. I rather focus today on the cognitive load that mutable state gives us, because these are things that you will notice in your everyday programming. If you take a look at the following code, we have a function that takes a car as an input. We print out what the car is, then we call a function print, and then we print out the car again. If car is mutable, do these two functions print, or do these two statements print the same thing? I don't know. The paint method might change the color of the car, or it may create a painting of a car. I don't know without actually having to go into the function to see what it does. And I kind of have to hope that there's not a whole function chain attached to it that I'll have to investigate just to know what this bit of code does. And this is the cognitive load that mutable state gives us. So let's make the car immutable. For this, we can use the records that Java 17 gave us, which creates getters for these properties, but not setters. So once we create an immutable car, we can no longer change any values. And if we now have this bit of code, where the immutable car is now our input, do these two statements print the same thing? Yes, they cannot do anything else, since the car is immutable, so they must print the same thing. So, and this is the powerful thing about immutable state. It reduces cognitive load. I can say things about this code without actually looking into the function paint. I just know these things. So values still have to change. And how do we do it with immutable state? Well, the only thing we can do is create a new instance of a car object that's an exact copy of the old car, except we paint it blue. And if we do that, our code now looks like this, where will these two print statements print the same thing? Probably really not, because there's a very obvious state change going on in between. And the nice thing is, I can even assign it to a new variable name to indicate the car is actually blue. So this doesn't solve every problem we have, but at least state changes are now extremely explicit. And now we have the option to use the old state or the option to use the new state. And these are just small patterns that immutable state brings us in our everyday code. However, with all nice things, there also come trade-offs. Because there is no silver bullet in software engineering, and anyone who tells you that there is either lying, trying to sell you something, or both. So the cost of this is performance. Because if you have to change objects a lot of times, you're creating a whole bunch of objects. And this, you can actually notice this sometimes. Although I must say, in my experience, for the average application, you won't really notice this. But sometimes you need to do weird things, like append 1,000,000 zeros to your input string. Well, there's actually a trick we can use here. As long as we keep the mutable state within function scope, the rest of the application can still see an immutable object coming in and an immutable object coming out. So as far as the rest of the application is concerned, it's just immutable state. So mutable state is great for performance gains. That's where mutable state shines. But you should try to keep it as much function scoped as possible, so the rest of the application doesn't see there is mutable state. And of course, make sure this function is thread safe. Another important thing about state is trying to make illegal states unrepresentable. Basically, try to make sure that the state of our object is correct. And one thing I really want to talk about there is nullable fields. Because I kind of hate null pointer exceptions, and I kind of assume that you guys do too. And nullable fields is a big cause of null pointer exceptions. So why are fields nullable? And not all fields are nullable fields are equal, because some fields are actually optional. For example, if you have a person, the middle name is optional. Like I have a middle name, but a lot of you probably don't have a middle name. So this is an example of a truly optional field. But not all nullable fields are actually optional fields. If you take this, for example, where we have a contract, which has a text and a nullable signature. Is that signature really a nullable field or optional field? No, because at some point in its life cycle, it becomes a signed contract. So it may be nullable in the beginning, but at some point, it shouldn't be nullable anymore. And the problem with this is that if we actually want to do something with the contract, like start a project, we now need to do null checks in our application and maybe throw exceptions. There's actually a better way to solve this. Yes, what's actually going on here is that the optional field, or that nullable field, is hiding a state change. And we can use our type system to reflect this. So instead of having a nullable field, we could also model these as two different types. We can model our state changes as types. We have a contract which only has a text, and we have a signed contract with a non-null text and a non-null signature. So it's no longer we have any nullable fields in our application. And better yet, we can use this trick to make architectural, we can show it architectural intent in our application. because our project can now ask for a signed contract. And that means we no longer need to do any null checks here, because the signature is by definition non-null. So here we can use a type system to eliminate nullable fields. It isn't a perfect solution for every case, but it's a very powerful thing to take away from this. So the key takeaways from state management is that state is difficult. And especially mutable state makes it more difficult because it adds the complexity of time. Mutable state isn't inherently bad because it's very useful for performance, but at least try to keep it as much function scoped as possible and have immutables in, immutable out. And we can use the power of our type system to get rid of nullable fields, and therefore reduce the amount of null pointer exceptions we have. So let's talk about error handling. The main thing here is that things will fail. So your connections will drop at some point, you'll get integer overflows at some point, things will go wrong. And you can basically divide all errors into basic categories. We have recoverable errors and unrecoverable errors. And I use a very broad sense of recoverable errors here. For example, we could use a default value if something went wrong. Or maybe there's an alternative code path, like my database isn't working, but there's like a cache I can speak to instead. Or if you have a validation error, a way to recover is actually returning a 400 exception saying what went wrong, so the user can fix it. So returning just a different status code is also a way of recovering. And on the other hand, we have unrecoverable errors. And these are usually everything that returns a 500 status code. So if a network connection drops, yeah, what you're going to do, you can retry it a few times, but at some point, you kind of just have to give it up. And I've seen three main strategies that people often use to deal with these errors. The first is just hope that they don't happen. This happens a lot, and hope is not really a valid strategy. The second that I see a lot is runtime exceptions, and I see a lot of cases where null is returned. So let's talk about what runtime exceptions actually are. So if we have our divide function, that takes two operands, two doubles, and it returns a double. But if b is 0, yeah, then we get division by 0 exception. Then the universe implodes. We don't want that. So we kind of want to throw a runtime exception in this case. The problem, however, is that the only reason that I know this runtime exception may occur is because I took the time to write some Javadoc. And of course, everybody writes Javadoc about these things. And everybody reads the Javadoc before calling a function. Otherwise, I hope you have good tests. So runtime exceptions basically do have disadvantages, because when you see this function, you think, oh, given two doubles, I return a double. But the behavior is, given two doubles, I might return a double, or I crash your current thread. Yes, that's what the runtime exception does. This, however, does make it great for unrecoverable errors. Because if you can't recover anyway, you might as well just crash the thread. So runtime exceptions aren't all bad. Another thing I see a lot is just functions returning null. Well, in this particular case, you might see the function returns null because returning a double with a capital, but in a lot of cases, this is not very visible. And again, you may be able to tell by the Javadoc it does that. But what I'm more concerned is, how do you deal with this null value? Because in a lot of cases, I see, oh, then the calling code now does a null check. So what happens if the value is null? It will probably return null itself. So now the function calling that function calls it. What does it do? It does a null check. What does it do if it comes null? I don't know, maybe return null as well. So before you know it, your entire function chain just consists of a whole bunch of null checks, which is quite ugly code, in my opinion. Luckily, there are some strategies against this, mainly being checked exceptions, optionals, and seal types. So, who here loves checked exceptions? Who here? One, two. Nice. Who here hates checked exceptions? Quite a few more people. The thing is, why do you hate checked exceptions? Because there are actually quite a few good things checked exceptions offer us. First of all, they show the method can fail, right there in the signature. It says that it either returns a string or it can throw that exception. It also shows that the function, in a way, has two return types, a happy path and an error path. It also offers the higher context a chance to recover. And with the runtime exception crashing the thread, basically this one says, oh, you either want to try to recover this or crash the thread anyway, but I'm not going to kill your current thread. It's up to you what to do. Also, the errors must be reasoned about. At some point, you do kind of need to do a try-catch around it. So you're forced to think about what's going on. They are also fully type-checked. So I need to deal with, in this case, a file not found exception. So checked exceptions are actually great for recoverable errors, things that can be recovered, because checked exceptions model this in a very good way. The only thing is that the API is absolutely horrendous. Nobody wants to put throws everywhere, and the try-catch is also quite an ugly way to deal with it. Luckily, since Java 8, we now have an alternative, namely the optional, which basically does exactly the same as a checked exception does. It returns either an empty optional or an optional which has a value. And it's displayed in the type signature that the function can go wrong. Also, it gives us a much better API to deal with the fact if it goes wrong, because it has nice methods like or else get, or even or else throws to recover from our error. And they're even very composable with the map and flat map feature, where you can only call the next function if the previous result went okay. The only downside here of optionals is that they lack error information. Good thing is, Java is getting some really cool features in the upcoming versions that can help us with that. Because just like signed contracts, where we modeled different state changes as types, we can also model function results as types. Because a function basically either returns a success or it can return a failure. So let's see what happens if we use our type system for that. Java 19 gives us sealed interfaces, where we can create a sealed interface result, which is either a success or a failure. And the fact that it's sealed means that the compiler knows these are the only two possible instances of the result interface, which will come in handy in a second. If we now rewrite our divide function to return an instance of result.failure containing a string with error information, or return an instance of result.success with actual result, in Java 21, we can now pattern match over this. So we can actually use our new switch statement to check if it was an instance of success, actually do this. If it was an instance of failure, do something else. And because we use a sealed type, if we ever add another thing to the result or remove one of these things, the compiler knows that this is no longer complete and will give an error. So we do not need the default statement here. If you want to know more about this, Hanno and Peter had a great talk about pattern matching, like I think it was yesterday. So take a good look at that. They go into far deeper than I'm going to get into it. But these are like the new features that I'm really excited about in the upcoming Java versions. So they give us a whole new way to do things like error handling. So the key takeaways from this is that think about your error paths. If they are recoverable, you may want to model that using checked exceptions, optionals, or sealed types. If they're not recoverable, runtime exceptions are fine. Just know that runtime exceptions are not the only option you have to actually do error management. And that brings us to our last topic, side effect management. So to talk about side effect management, we need to talk about pure functions. So pure function can be called pure if it has these three properties. That is idempotent, it's total, and it's referentially transparent. So what do these things mean? Idempotency means it's repeatable. given the same arguments, you will always get back the same result. Even if that result is an exception, that doesn't matter, as long as it's fully consistent. And if it's safe to call the function multiple times with the same arguments. A function being total means that for every possible input, it has a valid output, which kind of means that exception is not a valid output. Our plus function, for example, is total, because given any two operands, it will always return our new value. The divide function, for example, is not total, because if the second operand is 0, it needs to throw an exception. A trick we can use to make functions total are indeed these checked exceptions, optionals, or seal types. Because now at least your function always returns an optional. It might be empty, it might have value, but now it always returns an optional, making it total. And referentially transparent means that we can replace our entire function with just a lookup table. So if we have the plus function, we should be able to replace it with a huge table saying that if the first input argument is 1, the second is 1, then the result should be 2. Or if the first input is 1 and the second operand is 3, the result is 4. So if the function has this property, it means that it cannot alter any state outside of this function. It cannot do more than just a lookup would do. It can also not use any mutable state from outside of this function. Otherwise, the function might behave differently every time we call it, which means we couldn't replace it with this table. This also means that it's safe to just call that function anywhere in your code because it doesn't do anything apart from a lookup. And if a function has these 3 properties, we can call it pure. And that's a very good thing for a function to be, because pure functions are extremely reliable. They're very consistent, and therefore it makes it very easy to test. And by definitions, you never need to mock a pure function. And you can also make it static. So side effects are everything that makes a function not pure. Some very popular side effects are I/O, like reading or writing files, calling a web service, doing some database operations. But also, if you have setters, well, they change values outside of its function scope, so they're no longer referentially transparent. And if you have a getter attached to that, that getter now uses mutable states outside the function scope, so it's also no longer referentially transparent. Even logging writes to console or writes to file, so it also does side effects. You may think, yeah, it's going to be quite difficult to make an application without these things. Like, it's impossible to make an application without side effects. But they do have big disadvantages, because these are the things that make our code unreliable. These are the things that can fail. And these are the things that make our code very difficult to test. To give an example of that, how would you test this function? Where we calculate the number of seconds between now and the value we pass. How would you test this? That's the spoiler alert. But the thing here is, it's very difficult to test. Because on the second line of the function, we get the local data, we get the current time. So what's actually going on here is that the whole time is actually a hidden input into this function. And because it's a hidden input, it's very difficult to test. So the trick indeed is to turn a hidden input into an explicit input. So what if we change the function to this? So now the current time is an argument to our function. It's an explicit input, and suddenly your function is really easy to test. And now it's even a pure function. Of course, with modern mocking tools and such, there are ways to mock the local datetime.now. But I'm more of a person who, like, every problem can be solved, but it's always better if the problem doesn't exist in the first place. And one thing we can do to do that is making hidden inputs explicit inputs. Another thing I notice a lot is that business logic often gets mixed with side effects. So if we have this function foo, it takes a user from a database, then it does some arbitrary business logic, and then it stores the user in the database again. How would you test this function? Well, we can do that. but it's quite a bit of a hassle. We have to have either we have to mock the database, we have to have an in-memory database, or like with test containers, spin up a database. So then we need to make sure that whatever we did has the correct records, is in the correct state, and only then we can test this function. So it's possible, it's just quite a hassle. And there's basically a simple trick we can do. What if we put our business logic in a separate function? Now, if we still want to test the function foo, we still need to do all that. Like, that doesn't go away. But if we want to test our business logic now, hey, it just needs a user. It doesn't matter where this user comes from. So suddenly, our business logic is now pure and is incredibly easy to test. So the core bits of our programs are now very easily testable. And I call this the orchestrator pattern, where you have an orchestrator that basically deals with a side effect, gets something from a database, deals with all the things that can go wrong, does all the error handling and such, and only if that everything is okay, then it gives the value to our pure domain logic. That way, our logic doesn't need to do any error checking whatsoever. It can just focus on doing what it should do, doing business logic. Then it can just return a value, and the orchestrator can, for example, store it in a database again and deal with all the things that can go wrong there. And if we apply this pattern all over our application, what we'll get is a pure domain layer, which is extremely reliable and extremely testable. And around this is slowly an anti-corruption layer that deals with all the side effects. And if you will put this into a nice picture, it will look something like this. Where in the center we have a domain layer, around it an anti-corruption or application layer, and around that are the side effects, like database, web services, email services, and front end. And this picture might look a bit familiar. Hexagonal architecture. That's just side effect management. So for me, it's a bit weird that this is like all the hype right now, that it's a new thing, since it's just side effect management, which has been around for dozens of years now. But at least I'm happy that rebranding it helps, because now people are actually minding the side effects. But yeah, the whole reason why hexagonal architecture works is just because of side effect management. So the key takeaways here is that we can't build an application without side effects. And at some point, we need to do tests which include side effects. But at least we can try to identify where the side effects are. And either don't make it a hidden input, or from hidden input go to an explicit input, or at least separate our important business logic from them, so we can keep that as simple and testable as possible. And if we do this, we automatically move side effects to the edges, and you basically automatically get a hexagonal architecture. So what did we learn today? Composition is a very powerful tool that can help us with problem solving by dividing complex problems into sub-problems, solving those, and now we solve the whole problem. State is quite difficult. Be careful with that, and using immutability really helps a lot. Do not trust the happy path. Your software will fail. Hope is not a valid strategy, and there are other options and runtime exceptions. Be aware of your side effects and choose where they take place. And of course, be pragmatic, not dogmatic. If you have a very simple application, you don't really need these things. If, however, you have a big monolithic applications, you kind of need all these things to manage the complexity. And I kind of hope that you realize that you may be more of a functional programmer if you use any of these things than you might think you are. If you have any questions or would like to give me some feedback, this is the first time I'm giving the talk, I could really use some feedback, and even brought some stroopwafels to anyone who gives me some feedback, positive or negative. So please come to me after this talk. If you have any questions, I'll be around here all day. On my website, you can find all my previous recordings of talks and even slides. And if you just want the slides of this talk, you can find them on that URL. Thank you so much for your attention, and I hope you have a great last few talks in this conference.